Hello friends, I welcome you in lecture number 9 on vector calculus. In this lecture, we will discuss one more question on finding scalar potential for conservative vector field. This question was asked in GTU Summer 2020 exam for 7 marks. We are given one vector field f bar equal to y sin z minus sin xi plus x sin z plus 2yz plus xy cos z plus y square k, and we are asked to show that this vector field is conservative and find the corresponding scalar potential or potential function. So as we know, the vector field f bar is conservative if it is defined on all of R3 and if its component functions have continuous first order partial derivatives, and curl of this vector field f bar is a zero vector. Now if you observe here, these component functions are defined at all points in R3 because they are trigonometric and polynomial functions, and their partial derivatives of first order are also obviously continuous. So that we have written here clearly, f bar is defined on all of R3 and its component functions have continuous first partial derivatives in R3. So we now check what is this curl of this vector field f bar, and by the definition of curl of f bar is vector product of del operator with f bar, and this vector product is given by this determinant. First row is unit vectors I, j, k. Second row is components of del operator which are partial derivatives with respect to x, y, z, and third row consists of components of given vector field f bar. So we have written these three components as a third row. And now if we evaluate this determinant, first we start with I bar, and with I bar we have to write the determinant of this matrix, that is partial derivative of this function with respect to y minus partial derivative of this function with respect to z. So first we consider partial derivative of this function with respect to y, and at that time we will consider x and z as constants. So here x and cos z are considered as constants. Derivative of y is 1 plus derivative of y square is 2y. So we have x cos z plus 2y, that we have written here, x cos z plus 2y minus derivative of this with respect to z. So we consider x and y as constants. So here x is constant, derivative of sin z is cos z, so we have x cos z plus 2y constant, derivative of z is 1. So partial derivative of this function with respect to z will be x cos z plus 2y. So that we have written here, and that is to be multiplied with this unit vector I bar. Then we consider negative of j bar, and we consider determinant of this 2 by 2 matrix, which is obtained by deleting second column and first row. So we will now concentrate on these entries, and now this is we consider determinant of this matrix 2 by 2 matrix having these entries with negative of j. So first we differentiate this quantity with respect to x. We consider y and z as constants. So y cos z constant, derivative of x is 1 plus derivative of y square is 0. So from this we will have y cos z minus derivative of this quantity with respect to z. So we will consider x and y as constants. Here y is constant, derivative of sin z is cos z. So we have y cos z. So that we have written here, y cos z minus y cos z times j. And finally k bar is multiplied with determinant of this matrix. So first we differentiate this with respect to x, and derivative will be sin z constant, derivative of x is 1 and plus 0. So we have sin z only, minus derivative of this with respect to y. So we will treat x and z as constants. So sin z is constant, derivative of y is 1 minus 0. So here also we will have cos z. So that we have written here, sin z. Partial derivative of this with respect to y will be sin z, and partial derivative of this with respect to x will also be sin z. So we have sin z minus sin z, and we can see all these terms cancel each other. Therefore curl of f bar is a 0 vector, and hence f bar is a conservative vector field. Therefore we can write f bar as a gradient of some scalar function that we have denoted by f of x, y, z. Because f bar is a function of x, y, z, we write this scalar function small f as function of x, y, z. So now using this fact that f bar is gradient of f, we will try to decide what is this scalar function f of x, y, z, which is known as scalar potential for f bar. So now we substitute values of f bar, and we use the definition of gradient of f to write down the right hand side. So on left hand side we have written given vector field f bar. On right hand side we use the definition of gradient, which is del f by del xi plus del f by del yj plus del f by del z k. And now we have two equal vectors, and we know that two vectors are equal if their corresponding components are equal. So here coefficient of I is del f by del x, which must be equal to this coefficient of I, which is y sin z minus sin x. So we obtain this equation, del f by del x equal to y sin z minus sin x. Similarly coefficients of j are equal, so we have del f by del y equal to x sin z plus 2yz, and del f by del z will be equal to x y cos z plus y square. So we have obtained partial derivatives of required scalar function f of x, y, z, and using these three partial derivatives we will be able to decide this scalar potential f of x, y, z. Now if I want to integrate with respect to x, then I will consider this equation 1. Suppose I integrate equation 1 with respect to x, then left hand side will be f of x, y, z, and on right hand side, because I am integrating with respect to x partially, I will consider y and z as constants. So I can start with equation 1 by integrating with respect to x, and if I wish I can start with equation 2 also. If I start with equation 2, I have to integrate with respect to y, and if I wish to start with equation 3, I have to integrate with respect to z. So whenever we are integrating with respect to one variable, we will consider remaining two variables as constant. Okay, fine. So suppose we start with equation number 3. Suppose we integrate equation 3 with respect to z partially. Then on left hand side we have integral of del f by del z with respect to z. So that is going to be small f, that is f of x, y, z. And on right hand side we have integral with respect to z. And because integration is partially, constant of integration can be a function of remaining two variables x and y. So instead of writing plus c as constant of integration, we will write some function of x and y, say g of x, y, as constant of integration. Because we are integrating partially with respect to z, therefore we consider x and y as constants. Therefore the terms which contain x and y will be considered as constants. So therefore the constant of integration must be written as a function of x and y. So that we have written here, and here we have integral with respect to z. So integral of this with respect to z. plus constant of integration is considered as function of x and y. Here integral is with respect to z, so x into y is constant, and integral of cos z with respect to z is sin z. Similarly, integral of y square with respect to z. So because integral is with respect to z, y square is constant, and integral dz, that is y square into z. So that we have written here. So now we have our scalar function f of x by z, but we don't know what is this function of x and y, so that we have to decide. So this is not complete information about our scalar potential small f. We have to decide what is this function of x and y. So for that we can use any of remaining two equations. Suppose we want to use equation number 1, we will differentiate this equation with respect to x, because equation 1 gives us the value of del f by del x, and if we want to use equation number 2, we have to differentiate with respect to y. So suppose we differentiate this with respect to y, so we will consider x and z as constants, and because f is a function of 3 variables, left hand side is del f by del y, and on the right hand side here x into sin z is constant, derivative of y is 1. Here z is constant, derivative of y square is 2y, and because this is function of 2 variables and we are integrating with respect to y, here we will write del g by del y. So that I have written here, derivative of f with respect to y, which is partial derivative, x sin z as it is, derivative of y is 1, z as it is, derivative of y square is 2y, and because g is function of 2 variables, we have written partial derivative of g with respect to y. Now we put value of del f by del y from equation 2. Del f by del y is x sin z plus 2yz. So that value we substitute here, and that we have written from equation 2. So here we mention in the bracket, using equation number 2 we write del f by del y, which is x sin z plus 2yz, and this is equal to x sin z plus 2yz plus partial derivative of g with respect to y. So we can see these two quantities are equal, therefore we have partial derivative of g with respect to y equal to 0. That means this function of x and y, g, has partial derivative with respect to y as 0. Now suppose we want to obtain value of g from this equation, then we will integrate both sides with respect to y, because we have partial derivative of g with respect to y. Now we are integrating partially with respect to y, and g is a function of 2 variables x and y. Therefore we will consider x as constant, and therefore constant of integration can be a function of x also. So instead of writing simply constant c, we will write h of x, because we are integrating partially with respect to y. X is considered as constant, and therefore constant of integration can be a function of x also, and this is going to be gxy, and gxy equal to integral of 0 is 0 plus h of x. So we have found that g of xy is independent of y, it is a now function of x only. So now we again substitute value of gxy in equation number 4. So now our function f will be xy sin z plus y square z plus h of x. So that we have written here. Still we don't have complete information about this scalar function, because we are not aware about this, or we don't know what is this function h of x. H of x is an arbitrary function of x. So we have to decide this h of x also. After that we will have complete information about potential function. So to decide h of x, now we will use equation number 1, which we have not used so far. And in equation number 1 we have del f by del x, So we will differentiate this equation with respect to x, considering y and z as constant partial derivatives. So left hand side is partial derivative of f with respect to x. Here y sin z is constant, derivative of x is 1. This is independent of x, so its derivative is 0, and this is function of x only. Therefore we write ordinary derivative here, dh by dx. And now we put value of del f by del x from equation 1, which is y sin z minus sin x. So that we substitute here. Del f by del y is y sin z minus sin x equal to y sin z plus dh by dx. And if we take y sin z on this side, we have dh by dx equal to minus sin x. So we have obtained ordinary derivative of h with respect to x, and to obtain value of h from this equation, we will integrate both sides with respect to x. Now this h is function of x only, so we will write constant of integration as plus c. Okay, now constant of integration is arbitrary constant, so that I have written here integral of this derivative of h is h of x equal to minus integral of sin x plus c. Integral of sin x is minus cos x, and this negative sign is there, therefore minus minus plus cos x plus c. So this is the value of hx that we substitute in equation number 5, and our function will be xy sin z plus y square z plus cos x plus c. So this is the required scalar potential for given vector field f bar. And if we wish, we can verify this answer. We must have gradient of this scalar potential equal to given vector field. So this is the verification. I have verified whether gradient is equal to given vector field or not, and I obtained that gradient of f is equal to given vector field f bar. If you wish, you can also verify. First take partial derivative of f with respect to x, which is y sin z minus sin x, plus partial derivative of f with respect to y, so x sin z plus 2yz, and derivative with respect to z will be xy cos z plus y square, and this is equal to f bar. Therefore our answer is correct. So if you wish, you can verify your answer within half or 1 minute. So this is all about this session. I have discussed how to obtain scalar potential for a given vector field f bar, and the main thing which we are using to obtain this scalar potential is this equality, f bar equal to gradient of f. Using the definition of conservative vector field, we obtain these three equations: del f by del x, del f by del y, and del f by del z. This we obtain by comparing these two vectors, and this is the definition of scalar potential or conservative vector field. So after comparing these two vectors, we obtain partial derivatives of scalar function with respect to x, y, z, and integrating these equations either with respect to x, y or z, that is our choice. Here I started with equation number 3, so I integrate with respect to z. If you wish, you can start with equation 2 also. In that case, you have to integrate with respect to y, and you will use remaining two equations to obtain the value of arbitrary function. Here we integrated with respect to z, and we find that constant of integration is function of two variables x and y. Suppose we integrated with respect to y, then constant of integration was function of x and z, and if we started with equation 1, then in that case constant of integration was function of two variables y and z. So that is your choice. You can start with any of these three equations with which you are comfortable, and to obtain this arbitrary function of x and y, you have to use remaining two equations. So first we use equation number 3, then we use equation number 2, and then we use equation number 1 to obtain the value of this Hx, and we are able to decide our scalar potential. So this is all about this session. Generally they ask this type of question always. They always ask this type of question for 7 marks in GTU exam to decide the scalar potential function for a given vector field. So first you have to prove that given vector field is conservative. For that you may have 3 marks, and for the remaining part you may have 4 marks. So this is all about this session. I hope you like it. Thanks for watching.